So welcome everybody to our second talk for the year from Science by Diverse Scientists, which is our seminar series run through CalBridge and sponsored by the Research Corporation for Science Advancement. So today we're pleased to have Professor Christopher Gutiérrez with us from UCLA. So a little bit about his background. He's a professor in physics and astronomy at UCLA right now. He is from Los Angeles. He went to UCLA for undergrad, where he studied physics and mathematics with a minor in classics, actually. And then he went to do a master's at Cal State LA. So he's got all of the parts of our UC and CSU consortium here for CalBridge. He went to do his PhD at Columbia and was a postdoc at NIST and also the University of British Columbia before starting his current faculty position at UCLA. And apart from his scientific things, he is also an artist as well as a condensed matter physicist. And so he's going to be telling us about his journey in science and his research work today. Thank you very much for joining us, Christopher.
Thanks so much, David, for that really nice introduction. First, let me say how happy I am to be able to speak to everyone. Especially, as David said, being someone who has been an undergrad at UCLA, been a part of the CSU system. And I just realized now I have the triumvirate, because when I was in high school, I also attended Cerritos Community College. So I really have touched all forms of educational systems in Southern California, at least. And I'm was born and raised in LA, so really happy to be able to speak to CalBridge students and so many colleagues. So the outline for the talk for today, first of all, I'm going to talk about myself, my own background, my journey through academia. Then I'll talk about some of the research tools that we use, the things that I'm interested in. Specifically, I'll talk about some of the tools we use in my research group to visualize quantum matter, how we do that. And towards the end, I will talk about some, I'll touch on two kind of major themes of my research group project, where we're actually using these tools to not only image new phases of matter and new quantum behavior, but actually design them at the atomic scale as well. So first, as David mentioned, I'm from Los Angeles. Specifically, I'm from South Central LA. For those of you that are from LA and want to know, okay, South Central can be this really large area. Where are you from? I'm from an area that's called Florence Firestone, which is this red star down here. It's an area that's directly south of downtown LA, and it runs along South Central Avenue. So for those of you that grew up near there, you know that there's this large the central post office for Los Angeles. This is the area where I grew up in. My parents are Mexican immigrants. They're from a small town in Mexico, from the state of Zacatecas. Turns out there's a lot of people from Zacatecas in this area of Los Angeles, which is kind of interesting. But this is where I grew up. So like many children in this area, my parents were immigrants. My father was undocumented for many years until the 1980s. Luckily I was a child, so I didn't know about these, the stress that comes along with that. But like many other students, this is just this is what our life was growing up in that area. As I mentioned, when I was in high school, I attended community college once I made the decision that I wanted to study mathematics. I then went to my undergrad here at UCLA. I think in distance, it's only about something like 20 miles or so, but culturally and everything, socioeconomically, it's completely different. So growing up here and then attending college here is very, very different. It's two completely different worlds. When I was at UCLA, as David mentioned, I initially was a math major. Then I added physics as my second major. and also had a lifelong love of ancient Greek literature and myth. So I minored in classics. You're only in school once, so might as well, do all these things when you're an undergrad. Now, kind of the major thing, why this title slide is called my non-traditional path, is that it's a bit different than at least some of the other colleagues and friends that I had when I was in graduate school. And so, during my undergrad, I wasn't really sure, one, what I really wanted to do afterwards, and I didn't know whether I was prepared or not. After having done 2 majors and a minor, I was feeling some burnout as an undergrad. So I couldn't at that time imagine jumping straight to graduate school, especially with these questions that I had. So I actually I took a gap year after I graduated. And in that gap year, I had this very conscious decision I wanted to kind of get away from studying and kind of clear my head. So I actually did construction work with my dad, who's in construction. I'll talk about this later. And I put this asterisk here because this is something that everyone has to decide for themselves, but this should be something that you should discuss with a lot of different mentors and really, really think about it for a long time. So just to be clear, taking the gap year should be an individual decision, but just be prepared that if you take one, that there are some knock-on effects from that. I'll talk about this a little bit later. Now, during this gap year, I applied to graduate schools. I applied to probably too few and didn't get a lot of, I didn't seek enough guidance on how to apply to grad schools or how to actually think about that. And so of the 5 schools that I did apply to, I got rejected from all 5. Now, one thing that I knew was that I wasn't really a bad student. Oh, there's a question in the chat. Okay, no, it's not that I was a bad student, but I did have probably some, maybe a lower than average grade in 1 or 2 upper division courses. And so when these rejections came, I made this, I had to come up with a decision of what to do next. And so what I decided to do then was I decided to do my master's degree at Cal State LA. Let's go back one slide. So Cal State LA then is actually over here where this gold star is. So the colors of Cal State LA. So this is located in, I guess, northeast LA. Again, very different from where UCLA is on the west side. But it's a bit closer to where I had grown up. Now, there's several things that happened once I reached Cal State LA. Having been rejected from those schools, I made these conscious differences in my life. So one of them was I became a much more serious student. I made studying I made it a priority in my life, even though I had to work at the same time that I was a master's student. Luckily, I was very generous that I was a TA at Cal State LA, so I had some funding there, and I had actually some external scholarship and fellowships from Cal State LA, and that really, really benefited me. The other thing that I gained when I was at Cal State was some research experience that I didn't get when I was at UCLA as an undergrad, because being a first generation student, I didn't know that you're supposed to, seek out research experiences or talk to, instructors to get those experiences. So I fulfilled that at Cal State. I got some research experience doing some condensed matter theory calculations. The other thing that happened when I was a master's student was that I significantly improved my GRE score. There's an asterisk here because for many schools now, this is now being obsolete. And I completely agree with this decision. To give you a personal story of the GRE, the first time I took the exam, I took it with no studying at all. I just wanted to see how well I could do, without any preparation. And I got some low score. The second time that I took it, I prepared by studying all of my upper division coursework in physics. And I took the exam, I answered more questions. Somehow I got the exact same score. The third time that I took the exam, I said, ignoring everything that I learned as an undergraduate student, I instead studied the exam itself. So ETS has 4 practice exams. I literally just practiced those exam questions under test-like conditions, meaning I timed myself. I was really just increasing my speed of answering a particular type of physics question. And I got a significantly higher score. So what does that tell you? That tells you that I practiced to take a standardized exam. Had nothing to do with how much physics I learned, right? The two things were not related. So there's an asterisk here because I hope that this thing really gets eliminated from other, as some sort of piece in the admissions process. Okay, enough of my rant on GRE. So all these things that I did during my experience as a master's student at Cal State improved me as a student so much so that when I applied again after I graduated, this time I was accepted into 7 out of 10 grad programs. 3 of these schools were ones that had rejected me earlier. And I had written in the essay that, after being rejected, I became much more serious, which they could see in the improved GPA. Additionally, I took additional graduate courses at UCLA when I was a Cal State student. So after this, I did a PhD at Columbia in New York City. So, this kind of started my whole cross-country international move. So I broke my parents' hearts by moving from Los Angeles, where I had been my entire life, and moving to New York here for my PhD. After my PhD there at Columbia, which was an amazing experience living in New York City, I did my postdoctoral research in Washington, D.C. So here on the left, this is one of my most favorite places in DC. It's a very walkable city, and I would walk from the National Zoo over to the different memorials. And this is during cherry blossom season. After a postdoc here, this was at NIST, the National Institute of Science and Technology. I then did a second postdoc. I decided to change things up. So after learning all these scientific techniques, I decided I want to learn a brand new technique. So kind of a risky move. I feel like my story is peppered with these decisions to kind of radically change things. I decided to move to Vancouver, Canada to learn a brand new technique, which I'll mention later. And Vancouver is one of the most beautiful places on earth. So this was a really amazing experience as well. In both of these places, I really benefited from working with 2 of the best research advisors anyone could have in these 2 places. So I've been really lucky in my scientific journey to always be surrounded in scientific groups by really supportive, friendly people. So in terms of more non-traditional things, when I was a postdoc at NIST, and this slide is really for if there's any postdoctoral or graduate students watching, I decided to apply early for faculty positions, meaning I was really young. I was not even a year out of graduate school when I decided to apply. And different advice, some people said, oh, I don't know if that's a good idea. And other people said, sure, go for it. So with the support of letter writers, I decided, okay, I'm gonna apply early. I only applied to two places that I knew for sure that if they said yes, I would go. But I also didn't get any interviews that year. However, a few years later, when I did reapply, I saved all those documents that I had written before. It made the process so much easier. I could look back on it. I got earlier feedback on my applications, so that the second time that I applied, I got 5 faculty interviews out of only 9 applications and 3 offers. So really, I would say having this kind of preparation and this time in between these 2 admission search years kind of just really benefited. So finally, at the end of 2020, if we look at this little map of me traversing the country back to Vancouver and to Canada, in 2020, I finally arrived back home at UCLA here in my hometown. So I wanted to go back to the construction work because someone might think, okay, how did this benefit doing a gap year, doing construction work? It turns out this is one of the most valuable experiences of my entire life. So this is a photo of me and my dad. What we're building here is actually an extension of our own house. This was one of the projects that we worked on, and not only was this amazing in terms of spending so much time with my father and where he works, but I learned a lot about being a better experimental physicist doing this. So some of the things that overlap that are the same from being doing construction work and being an experimental scientist is that every day, preparing for every day being different. Meaning some days we're digging and pouring the foundation, or other days we're doing a lot more planning of how we're going to do some of the framing for the house or some of the electrical wiring. Every day is different, which kind of made me much more prepared and excited about being an experimental physicist, where every day it is different in the same way. It made me really appreciate safety, especially with electrical things. You're dealing with moving really, really heavy objects. In my case, as an experimental physicist, these are things that are still important to me. The other one was collaboration was key. So never trying to do more than what you're capable of doing, meaning lifting something heavy. You have to talk, repeat, you have to be in really, really good communication with the crew that you're in about these things, asking a lot of questions of what you're doing. So this is a really, really important thing to learn. The other one was patience in the face of obstacles, meaning that if something went wrong, and it, sometimes it does on a construction site, that there's no panicking, that it's just, put your head down and you attack the problem then and there. This is one of the most valuable things I learned for being an experimental physicist, that when problems show up, it's okay, that it's totally okay when problems show up. You just deal with them as they come. And the best one was the satisfaction of a completed project. So, this is a new room in our home, and it's still there, and it's safe, and it's something that when I look at it, I think I was a part of doing this. It's a really, really fulfilling feeling to have. So all these things, whatever your path may take you, it might not be construction or something else. You really can extract all these things and apply them towards yourself as a scientist. No experience is ever wasted. And so kind of the main message that I would have for any student is to bring and be your whole self. This is, again, this is me as a teenager in South Central LA. As David mentioned, I'm also an artist. This is something that's really important to me. And so folding in being an artist into being a scientist is something that I do in the laboratory. And so, as opposed to drawing pictures of my friends, making portraits of them, having this skill of being an artist has really benefited me in terms of being able to communicate my science and scientific discoveries. So here I have examples of some of the cover art where my artwork or art skills have been used to communicate science. And for those of you that are interested, I've created a whole series of free web tutorials to teach these skills of how to make scientific artwork. So all of us have, our own unique backgrounds. We all have our own unique skills, and so that really kind of enriches our lives as scientists, because we can bring those things into the laboratory. So yeah, so the main message that one of the main lessons that there is no just one path, right? You don't have to pay attention to what other people are doing or what schools are going to. It's just, we have our own path, and it doesn't matter how long it takes to get there. And so all those the experiences that you gain along the way, you can always leverage those as, your new and unique strengths in your path. Okay, so with that, biographical sketch, I'm not going to talk about some of the things that we do in my laboratory and some of the things that I'm interested in studying in my research group. So I'm a condensed matter physicist. What that means is I study systems where the whole can be very, very different than the individual components. So it's really the study of emergent phenomena. So if we study, the electron was discovered, 100 years or so ago, a single electron can be very boring, but if you put groups of them together, they can act very, very differently than just any individual electron. So really, it's about the emergence of new behavior that can happen when you have groupings of these things. And so besides being a field of fundamental interest, right, we're still studying the universe by studying the electrons inside of materials. What's really amazing about condensed matter physics is that it has direct applications to things that can really impact human civilization. So some of those things are studying materials for energy efficient, either transmission of electricity by studying things like superconductors. So these are materials where there's zero resistance, so no loss in energy transmission. By making ultra-sensitive quantum sensors for either detecting signals or for quantum information, so making quantum bits or as parts of a quantum computer, or things like making materials for efficient energy harvesting, so turning the energy from the sun into electricity, so sustainable energy. All of these things are amazing end goals of studying condensed matter physics that have direct impacts on us as a society. So my particular, interest in condensed matter physics is I want to understand actually how the tiny little atomic defects in all of these materials, how do they affect real materials? So no material is ever perfect. There's always going to be tiny little defects in them. So my interest is really, how do those tiny little defects affect those, big macroscopic electronic properties? And secondly, once we know how those defects affect those properties, can we then re-engineer? Can we then design? Can we purposely design new behavior or new phases of matter by altering the materials, by purposely, designing those defects, putting them in different places or moving them around? This is my particular interest in condensed matter physics. And to give you some historical viewpoint of what, you might think, okay, defects, who cares? So to give some historical context, the semiconductor revolution, right? The chips that are inside of our phones right now, the very first transistor had about 1 transistor per square inch. This is from, this was the first transistor from Bell Labs. This is literally a chunk of germanium with a plunger pressing down on it. Before we could understand the behavior of a single transistor, we really had to understand how defects inside of germanium behaved. How did defects inside of germanium affect the electronic properties? Once this was understood, this really unlocked our understanding of semiconductors, where we could go from 1 transistor per square inch, so this thing can fit in the palm of your hand, to having something like 300 million transistors per square millimeter inside of our, inside the technology that you're watching me with right now. So understanding defects in materials can have really, really huge impacts. And so I study quantum materials. You might be wondering, so what is that? So these are materials where we have these emergent quantum properties, but at the human scale. So either the human scale or at room temperature, we usually think of quantum effects occurring at things that are really, really small or really, really cold. But sometimes they occur even at the human scale. So good examples of that are things like high temperature superconductors. So this is a superconducting sample hovering above a magnet, kind of like the image that I showed you before. Another quantum material is graphene, where we see these quantum effects, again, at this macroscopic scale. Graphene is an interesting property that we use that we study in my group a lot, where it is a single layer of graphite, the same graphite that is in your pencil lead right now. And it looks kind of like this. These are carbon atoms and this kind of chicken wire honeycomb lattice. In my specific group, we study materials like graphene. These are called two-dimensional materials because they all consist of layers that are either purely two-dimensional or they can be cleaved easily, right, into sheets, kind of like paper. Some of you might have heard that Scotch tape method. We literally, we do use things like Scotch tape to separate these layers into single monolayers of these bulk materials. Why do we study these things? Well, these materials are highly tunable, meaning that we can change many of their properties by doing different things. We can apply a voltage to them to change the number of electrons that are inside of them. This contrasts with other systems where you literally have to grow crystals. If you want to change the number of electrons in a system, in the past, what you have to do is to literally grow a crystal that has more electrons by putting either donor atoms in there or something like that. Here, you literally just apply a voltage. So it's very easily, you can change the electron density in these systems. You can change your properties by stacking them, like sheets of colored paper. You can just shuffle them and change their properties that way by coming up with new and interesting stacking orders. You can do things like twisting them. So once they're stacked on top of each other, you can twist them to create all new types of patterns. So there's really numerous possibilities to tuning these materials. As I mentioned earlier, I was an Emin artist. And so, really my interest in these materials is changing things, taking a material where I know what the properties are, and then finding ways to tweak them. This is really my interest. So I mentioned imaging the quantum world. That's in the title of the talk. So how do we see the quantum world? For those of you that might have taken some quantum mechanics, you know that the size of the electron is much, much smaller than the wavelength of visible light. So how do we see these things? Well, we can use quantum mechanics to actually see the quantum world. So in quantum mechanics, if we start from a classical object, so some large ball, our everyday experience is that if we send a ball at a wall, at some barrier, what we get is that the ball is reflected back at us. In quantum mechanics, the same thing happens. We can send some quantum object at a barrier, some sort of wall, and we might measure something coming back at us. However, in quantum mechanics, it also turns out, since it's probabilistic, there's a really small but finite chance that the quantum object can go straight through the barrier. And we call this quantum tunneling. So even though we're sending this quantum object at the barrier, there's a really small chance that it's on the other side of the barrier. Now, how we can use this to actually image electrons is we get a really sharp tip. We put it next to some sample that we're really interested in. We apply a voltage between these things. And what we can measure is this tunneling current, this quantum tunneling current from electrons from or to the tip to the sample. Now, obviously, since the chances of the object tunneling across the barrier is really small, the tunnel current that we measure is extremely small. It's usually on the orders of picoamps. So this is 100 picoamps. So this is 10 to the minus 10 amps. And if you're wondering how small that is, the current in your refrigerator right now in your kitchen is about 6 amps, or it's 60 billion times larger than the tunneling current that we measure in the laboratory. So the way that scanning tunneling microscopy works is we start quantum tunneling and we ask a computer to maintain that current as we raster the tip across the surface. So it's a bit like how one would read Braille, right? With Braille, you raster your finger and you feel the bumps. So here our tip is feeling the quantum tunneling signal. And what you get is this beautiful atomic image like this. So if we looked at just a single line of this data, it would look like these bumps. So if we stack all these curves on top of each other, we can make these beautiful atomic images. This is the surface of graphene, that atomic system that I showed you earlier. And you can see if we zoom in, we can see this honeycomb structure. So, you know, the atoms in these systems look like what you learned in chemistry class. Now, this specific image of graphene was chosen because there's a defect in it. There's a missing carbon atom somewhere. Now, the really interesting thing that you can see is that near, you know, far away from this defect, you get a perfect honeycomb lattice. But near it, if you kind of maybe squint, you can see that there's these ripples, right? You can see these kind of, if you really squint your eyes, you can see these ripples in the graphene itself. Those ripples are the electrons themselves. Since electrons are quantum mechanical objects, they're not exactly particles, they can be described as waves. And so the electrons themselves are rippled in the surface of graphene. And so really this is the strength of STM, of scanning tunneling microscopy. It's not that we can just see the atoms, right? There's other tools that can do that. Here we can visualize the electrons themselves and their wave-like properties. So just like dropping a water droplet on the surface of a pond and observing the ripples, what you can do with a defect, so this is a defect on the surface of copper, this defect, like the droplet, creates ripples in the sea of electrons that live on the surface of the material. This is an image of one ripple. This is another top view. So this looks like ripples in water, but instead what's rippling here are the electrons themselves. Now I'm going to give a 1 minute kind of background to solid state physics just so we can understand the preceding slides. You know, when you have ripples, right, we can describe this by some sorts of periodic structure, some sort of wavelength. But it turns out for solid state physicists, instead of working with wavelength, so, you know, lambda, it's easier for us to deal with K, or the wave vector. The wave vector K describes those ripples of the electrons. Now, using the de Broglie relation, we can relate some sort of momentum to that wave vector or the ripples. So for free electrons, you know, this is just if we look at the kinetic energy term, we get p squared over 2m. This is the same thing as 1/2 mv squared. If we were to plot this for some sort of free electron, we would get this parabola. Right? We would get a simple relationship between energy and momentum. It would look like this. But inside of a crystal, when electrons are inside of a crystal, this relationship could be much more complicated. Right? We call this the dispersion relation or the band structure. So if you're ever in a talk with a condensed matter physicist and they measure band and they say dispersion relation or band structure, what they mean is the relationship between energy and momentum. Crystal momentum, or the relationship between energy and the ripples of the electrons in the material. Okay, just wanted to kind of give this background. Now, I just mentioned STM. The other technique that we use in my group is angle-resolved photoemission. So here we can literally measure that relationship between the energy of an electron and its momentum. And instead of the quantum tunneling effect, here our measurement is really based on the photoelectric effect. So we shine light on a system, we eject an electron, and then we can measure that electron's momentum coming off of the surface and its kinetic energy. So we can make these images that directly look at this band structure or the energy momentum relationship of the electrons. So I'll next, having described those two methods, I'll talk about these two kind of themes or projects in my research group, where we're going to design new quantum behavior in interesting materials. So one broad theme in my group is we study density waves. Density waves are found in many different fields. Density waves can be found to describe the arms and galaxies. For anyone that's been in heavy traffic, there's density waves there, except it's of cars that travel backwards when you're in traffic. But the density waves that I'm interested in are the ones that occur inside of materials. So just like the name says, in terms of density wave, here what's changing is the charge density. So it's the positions of where the electrons are huddling in space is somehow modulated. So if we look at a cartoon picture of a regular metal, in a charge density wave, some of the atoms become closer together, which means some of the electrons get huddled together. And using the STM, we can actually visualize, what is the structure of this density wave. So we can see that every third atom here on the surface of this material is dark. So this is a charge density wave system. So the STM, we can actually see these materials. Now, density waves are interesting because they appear in a lot of other interesting materials, such as materials that superconduct at room temperature. So by studying really simple systems where CDWs happen, maybe we can learn more about their behavior in much more complicated systems. And so in my group, we study how density waves form in graphene, where graphene is a very simple system. You only have carbon, and we know the exact geometry of the graphene lattice. So this is a kind of an interesting system to study, an interesting and clean system to study density wave formation. Now there's kind of a famous density wave distortion in graphene called this Kekulé distortion, where some of the atoms, kind of like I showed you that picture before in 1D, some of the atoms get closer to each other than others. And this is called the Kekulé distortion. It's named after Friedrich Kekulé, who hypothesized the structure of benzene, because each one of these little units looks like a benzene ring. So using what we've known in the past, that defects can create these ripples, one question that we asked was, well, if we created a ripple on graphene, right? Graphene has a very different relationship between energy and momentum. It's not like a free electron. It has what's called Dirac cones, this kind of triangular cone-like structure. And there's two of these cones describing the electron momentum relationship. So one question we asked was, well, what if we added defects to the surface of graphene? Could it induce an entire density wave throughout the entire material? And so this is kind of a cartoon picture. This is a simulation I made, where we're looking at around each one of these defects, if we give some puddle of this density wave distortion that's created near it, what we found is that even if you add a few defects to the surface, you get areas like this that are in between the defects, where this puddle of density wave order actually grows and becomes coherent, right? Imagine we're stacking all of these density wave puddles right on top of each other. What happens is that even though you have very few defects on the surface, you get this reinforcement of density wave puddle throughout the entire sample. And so what we found by using our STM is we can literally image where these defects are on the surface. And we can add a kind of color code that tells us, okay, these defects are on the same type of site, the type of site that would give us this long range order. And what we found surprisingly, right, is that the reason why we see density wave order very, very far away, we see it in the entire system, even though we only have 1% defects on the surface, is exactly because of this, because the defects these single defects can move, they can jump around, but when they settle down, what they want to do is they want to all sit on a blue site such that they create this kind of long range density wave order. Sorry. What slide am I on? There we go. And so this work, which I showed earlier, this is work from my PhD. We showed that this density wave order could be seen in graphene. So the important thing was that this density wave behavior in single layer graphene hadn't never been seen before. And it's caused by a very, very few number of defects on the surface. by heating up the sample, these T-effects move around and they create this long-range order. And this work was highlighted on the cover of Nature Physics. Now, just quickly, I just want to talk about some of our most recent work in our group. Turns out that the work from my PhD created a unique phase where the bond geometry looked like this Y shape here. And you can actually see that in the previous slides, that the bonds look like this Y shape. This isn't the one that had been predicted for a long time. So actually what we viewed was this brand new phase that hadn't been predicted. But that phase is very different than the one that had been predicted and that has unique properties. So one example is that this the phase that we accidentally discovered has no energy gap. So there is no there are no overlap. The relationship between energy and momentum, there's always an energy state available to the system. Whereas what we would like to see is an energy gap where there are no electrons, because that can turn our system from something that's a metal and conducts electricity to an insulator and doesn't conduct electricity. So what we attempted to do later was to purposely create the type of Kekulé phase that we wanted, the kind that actually has an energy gap. And just in one slide, I just want to show you that we had this breakthrough, that these results are currently under review. And here, instead of using STM, we actually used ARPAs, we used photo emission. We directly imaged the momentum, the energy momentum relation of the electrons in the regular graphing phase and also in its density wave phase. And here we purposely created the phase by peppering the surface with a very, very small amount of defects. So actually an order of magnitude less, so on the order of 0.3% of defects on the surface. So it's an extremely small amount. So even though you have a small amount of defects, it really changes the entire properties of the system in a global sense. Okay, so I mentioned that we use defects to create these, new phases of matter. So that was the Kekulé distortion. Now, the other thing that we can do with defects is that we can create artificial atoms. Now, you might ask yourself, how does one create atoms, right? So you can either find atoms, at the center of stars. So stars are a good way to create new atoms. This is an image of my colleagues' ion traps. So these are some floating ions that are being controlled with magnetic fields, with laser light and magnetic fields. But what I'll talk about next is that there is a way to use the STM tip to create an atom. Now, not a real atom like the kind that you can find inside of stars, but an artificial atom. So what is an artificial atom, right? Another name for artificial atoms are quantum dots. And these are the same kind of quantum dots that are actually in some of your TV screens right now. So what is an atom? So an atom, is a collection of particles that are in some sort of, potential, right? So when we look at the behavior of atoms, these are some electrons that are confined to some really, really small positions in space, so something like an angstrom. In artificial atoms or quantum dots, what we're doing is we're confining electrons to something with much, much higher spatial confinement. So something in the order of 10, something like 10 to 1,000 times larger than an atom. But they're still being confined. Right? So when we solve the Schrodinger equation for atoms, we get this quantized energy behavior from the confinement. And we see the same kind of confinement in quantum dots. So whereas in atoms, the energy spacing between the levels, right, it's due to this Coulombic confinement. Here in atoms, you have well-spaced and discretized energy levels. In quantum dots, artificial atoms, we see the same thing. So we see this quantized energy behavior. Sometimes this can be seen in current and gate voltage or in energy, which I'll show you in the next few slides. So how does one create quantum dots? Sometimes, like my colleague, Professor Hongwen Zhang here at UCLA, you can use sophisticated deposition techniques to deposit metals on the surface of materials, and you can electrostatically confine puddles of electrons on the surface of these materials. Here, the quantum dots are on the order of 100 nanometers. But with the STM tip, actually, we can save all of this, possibly complicated surface design of these quantum dots by simply using the STM tip to create these quantum dots. Now, this method was created at Berkeley, but it's now been used at several groups, including now here at UCLA. Here, what we do is that instead of depositing metals to try to trap the electrons, we use the tip. We hover it over a piece of graphene and we give it a voltage zap. That voltage zap creates the potential that we need to trap our electrons. And so the way that I like to think about it is that our tip hovers over graphene. We give a voltage zap. We attract defects that naturally exist inside of the substrate. This substrate is boron nitride, which is an insulator. All of those defects get, so some of those defects, the ones that are underneath the tip, get ionized and they get attracted to where the tip is. So this is actually very similar to how the magnetoodle works. So if any of you have ever played with the magnetoodle, it was one of my favorite toys as a child. The magnetoodle has these iron filaments inside of some goopy material. You bring the stylus, which has a magnetic tip close to it, and it attracts those defects. It attracts those magnetic filaments. So in my group, we're using the STM tip similar to how a magnetoodle works, except instead of drawing funny patterns, what we're drawing are custom electronic potentials to trap electrons. Once we trap those electrons into this potential, we then use the STM tip to then directly visualize their energy structure. And so to give you, an idea of how this works, with the STM tip, we can vary the voltage at which those electrons are tunneling into the sample. And so similar to peering into a cake, right? So let's think of the analogy of electrons with their quantized energy levels. A quantum dot should have a similar type of discrete energy level. So using the STM tip, we can get all this, multi-dimensional data. And now by slicing the data into different dimensions, we can look at the quantum dot behavior. So if we had a cake, if we sliced a single slice, so meaning at a constant energy, we can ask the question of where are the electrons? What is the probability amplitude of where those electrons are at a specific quantized energy level? So here in the green slice, this is a horizontal slice, we can directly image where the electrons are inside of our potential trap. Notice that they're making these beautiful concentric rings. So everything that is bright here is telling us where the electrons are in our sample. And you can see some of the wave-like behavior. The other thing we can do is we can take what's called a vertical slice, or we're looking at the tunneling energy as a function of distance. This is kind of like taking our cake and looking at a vertical slice. So this gives us information on where the energy levels are, right, in the vertical axes, and then where the electrons are as a function of those energies. So we can see that there's, we can actually see the spacing in the quantized energy levels of our electrons. Now we can take this analogy actually further. We can start to, because we can actually enumerate the quantum wave functions, we can actually enumerate these quantum these quantum dot states in analogy with the hydrogen atomic state. So the first quantum dot state has no node in it, just like the S wave orbital. The n equals 2 and the higher energy quantized energy states in our quantum dot have increasingly numbers of nodes in it, just like in the artificial atomic state. Now, the amazing thing, right, is that since this is an artificial system, it actually provides us a way to study atomic states, but in a system that doesn't exist normally. The electrons in graphene behave very differently than other systems. So this really gives us unique control over a system. Not only control in designing the atom itself, but then visualizing those atomic wave functions. And so what are things that we can control once we create these dots? Well, one thing we can do is we can then control the energy levels by applying a magnetic field. So we can do really cool things like asking, well, we know from our quantum mechanics classes that once we apply a magnetic field that we should see something like Landau levels. We should see these atomic-like states melt or condense into some sort of magnetic Landau level state. And this is exactly what we see. So here, this is a view of our all of our atomic energy levels as we increase the magnetic field. So we notice that at really small fields, right, we just see a splitting in the states, not too interesting, but at really high fields, these individual atomic states then condense into a highly degenerate Landau levels here. Remember, these three are vertical views of energy versus space, but if we do a top-down view, we can then see that these Landau levels are forming these kind of 1D, these kind of one-dimensional skipping states of electrons traversing the edges of our quantum dot. So like a race, the electrons are now moving in circles around our quantum dot. And so the next steps that we have in terms of our project with regards to quantum dots is one, to create quantum dots using other materials. So graphene isn't the only system. There are much more interesting materials that have energy band gaps where we can better trap those electrons, possibly for other uses such as for storing quantum information, possibly. The other thing is to study even a smaller quantum dots. So some of the smallest ones that we can see actually have atomic dimensions. This is a very small quantum dot where you can actually see the atoms inside the system. So we can now study how those large-scale wave functions depend on the atomic details of the system of the dot. And our future work is trying to create multiple of these dots and actually couple them together to try to couple them to create something like artificial molecules, where we can directly visualize the molecular bonding states between these artificial atoms. So this is all the kind of giving you all a brief view of what we do in our research group, but to bring it all back, right? So this was my individual path in physics, and what I'm hoping is that by giving you an example of my unique path is that you know that there is no one path for everybody. And again, all of you are individual. You all have your own individual strengths and experiences, and all of these things will really enrich your life as a scientist. And with that, I thank you all.
Okay. Thank you very much for that talk, Christopher. Let's give a virtual round of applause. So at this point, we're open for questions. So for everybody's on the line, we've got the Q&A thing at the bottom. So you'll feel free to type any questions you have in there. And also, well, panelists here can also ask questions if you want. Maybe I'll start off with just kind of a something amusing. And so I as you mentioned that you studied classics, I actually studied ancient Greek when I was in college. At the same time when I was taking solid state physics, there was actually one guy who was in both of my classes at the same time. We were comparing notes on what led us to that, but also it's interesting to think of, you're dealing with all these Greek letters in science where you think of, a totally different point of view of how they are, how they make up words in the Greek language instead. One thing I was very struck by was the word phonon. So I guess you didn't end up coming up in what you've talked about here, but right, for everybody else, it's vibrations in condensed matter we call phonons. Do you know what that means in Greek?
Specifically, I mean, phono would come from sound, right?
That's what they meant to do in coming up with this word, but it actually turns out phonon, just exactly as this word is it means murder in ancient Greek.
Because they added the n at the end, the new. Is that why?
Yeah. That is a word that Aristotle or anybody else would have understood. So I always like to mention this in my classes when Halloween is coming up.
Wow, I'm actually teaching
murder.
I'm teaching solid state now, so I'll.
Yeah, you can tell that even better. A spectrum is a ghost. So.
Yeah, from spectra. Yeah.
So we've got ghosts and murders going on.
Having the humanities background. So did you take several courses in classics, or?
I took four quarters, I guess, in total.
Yeah. I think it really benefited me when I was an undergrad. It really chopped up my heavy math and physics classes to have humanities. It's actually shaped the way that I am as a teacher now, because the way that I teach comes more from humanities than it does physics. And I've told my classes before, which is in your humanities courses, you don't go to class and read the book together or rewrite the book on the whiteboard, and so you discuss key points from the text. And so I think this is kind of, taking those courses really kind of changed the way that I teach as well. The students that are taking my class now will be the judge of whether how successful that is, though.
Fair enough. Who else has a question or comments?
The questions can be about physics or my background.
Could I ask a GRE question?
Yeah, sure.
So I know this year, because I know one of my students is in the audience, and so this is partly for his. We were just talking about the GRE and how it's been going away. Do you know at UCLA if in the future they're planning on using it? Because I know some places have just gotten rid of it because of COVID, but then.
That's right. I think ours has it's suspended. It was suspended for COVID. I don't know about the future. But my position is clear that I don't think it really serves much. Yeah, it's an extra cost, and I don't know that it tells you that much.
Yeah, agreed.
Yeah, I always tell my students, it's not like when you submit a research paper, do you put your your GRE score? No one cares. If there are Cal State students in the audience, things have changed a little bit. I would have to look back, but the program that I used in order to take UC graduate courses at the same time as being a Cal State student was called concurrent enrollment, open doors. You'd have to check yourself to see if it's been updated to allow for graduate courses. Back when I was a student, it was allowed. The nice thing about concurrent enrollment, Alex, do you have the answer?
It is allowed, and we even talked about making it a feature of the program.
Oh,
but we just never were able to. I mean, it's funny because now that we're in the middle of COVID, it would have actually been, at the time we first thought about it, it was sort of like, well, is somebody going to really schlep over to this other campus?
Yeah.
To take this one class, it's on quarters rather than semesters. Now that we're on COVID times and people are more used to these kind of virtual things, we could revisit that and think about, if not making it a formal feature, making people more aware of it. So that's something which we were aware of, and it's apparently very, very cheap. It's sort of like built in that there's this law that it's only like $40 a unit or some ridiculously low price.
Exactly. So the thing that I benefited from the program was that, and it's really nice the way that it was written into law, I guess, is that if you're enrolled as a Cal State student, you don't have to pay so much for those UC courses, because the idea being you're already enrolled, so you don't get
Right.
charged twice.
Right.
And so
exactly.
the amount that you pay per unit is pretty good.
Pretty
And I
low,
believe
yeah.
the maximum at the time was 2 courses per year, which is
Right.
totally fine.
I
Yeah.
think the other thing that, I don't know if this is true when you were going, but as you said, LA has a master's program, and a lot of CSUs do, and so they were sort of have their own graduate. If you were sort of an advanced undergrad, you could take a local grad course. That's not to say though that there might not be a specialized course that would be of particular interest. And I think one of the ways we might look at that is to see if letting the faculty mentors know that's an option, so that like the UC faculty could say, hey, maybe you want to think about this course or that course as part of your background. And I'd be curious to know how the UC faculty think that would be looked at in the application. That is, would it be seen as like, wow, well, they can take and do well in our classes? Would that make a difference? Or would it be more like, well, okay, it was just one class, so it doesn't. So that would be an interesting question to ask some of the UC faculty as well.
Yeah. I think when I was at Cal State, it was still quarter system. It hadn't transitioned to semester, so it was a bit easier back then to.
Right. Yeah. So we just recently, all the Cal States basically went over semesters except for San Luis Obispo, because most of them were semesters at that time. Yeah. LA, Pomona, San Bernardino, a bunch of us used to be quarters, and now we're all semesters. So, but that's not an insuperable problem. It's just something to think about.
Yeah, and definitely this program is not well known. I remember when I was doing this, other people at Cal State didn't know that it existed. And even when I graduated, one of my colleagues at Columbia, his mother was a professor at Cal State. And I had no idea that this program existed of concurrent enrollment.
Yeah.
And so I forwarded her the information. Yeah. So I think making it, highlighting it to students as one option if they wanted to, like you said, take an extra class that possibly isn't given, I think would be really great.
I have a question. I mean, clearly your art has informed your science, at least your Nature covers and other magazine covers. But do you think there's a way in which being an artist has sort of impacted your ability to, say, visualize? Because one of the tricks in physics is it's a bit, you actually have pictures now, you can make images, but you're still trying to visualize these sort of weird quantum things. And does your artwork, you think, has that improved your ability to visualize and sort of think abstractly about these sort of weird states? Or is it more just something you enjoy that you bring to your work in science?
That's a good question. I would say, I think it does. I think it does inform. I think it has improved. Meaning that sometimes when we're looking at our data, you can see where the wiggles are. You can see where there's interesting things happening. And so I don't know that specifically that it's having this artist background has improved that. At least the ability to kind of detect or see these things right away. It definitely helps with communicating. So finding the right color scale to effectively display what you want to show, and in a way that is cognizant of people with color blindness, especially. I won't give any examples, but there's certain papers, right? Just like, why did you use that color scale? It's hiding all the things you want to show. It's using a linear color scale. So our eyes can detect better things when you see this gradual change in the intensity of a color versus sometimes the subtle changes between colors, especially in the green region. And so these are things that, there's so many better talks on this than from me, but purely as an artist, when I see aesthetically a bad color scale, I just kind of cringe. Yeah, it could be explained in a much, much better way. So there is some effect, I would say.
Did you want to come full circle and draw the analogy between the defects in the materials and like sort of personal journey anymore? Like, how does that?
Yeah, exactly. So I didn't make it as explicit as it is in the abstract, but really, these kind of the really main theme in my group is, and especially in this work, is that these tiny little defects at key positions in the lattice create this brand new thing in the entire system, and it's global. And really, these kind of defects or obstacles at key points in my life have really kind of changed me as a person. When I talk to students, if they're going through obstacles, like me being rejected from every school as an undergrad, I knew that I was better than what was probably reflected because I maybe got a C in upper division E&M, right? In your transcript, it doesn't say what was going through your life at the time, and all you are is this piece of paper. But having that happen specifically at that time really crystallized me, becoming a much more serious student. All these other hiccups along the way, going to Vancouver and really changed me as a scientist. All these kind of things that we sometimes think are bad things, right? These doing construction work for a year. These things have actually made me a much, much better scientist. And it's really, if anything, kind of accepting our defects, right, as being key experiences that shape us as a person. Yeah. Thanks, Aaron, for letting me bring that all back together.
Well, since we brought everything full circle, I think that's probably a good time to bring this session to a close. So thanks again very much for joining us, Christopher, and talking to us here today.
Thank you.
And everybody tune in 2 weeks again for the next seminar in our series. And have a good evening.
Thanks.